An architectural blueprint is pristine. It exists as a geometry of exact tolerances. But translating those lines into thousands of pounds of reinforced structural concrete requires the brute force of heavy industrial manufacturing. The precast industry operates inside highly rigid physical parameters. You are constrained by the physical footprint of fixed-length casting beds, often stretching 100 meters across a factory floor, and strictly enforced chemical curing times. When you attempt to manage these inflexible variables through manual calculation and human intuition, you hit an immediate mathematical bottleneck. The inefficiencies compound quickly across the supply chain. Unoptimized casting schedules lead to severe raw material waste. Unpredictable production rates inflate inventory holding costs, and manual drafting errors guarantee highly expensive factory reworks. Achieving high-yield production in this environment requires stripping the manufacturing process down to its data points and deconstructing the traditional, siloed pipeline. This diagram illustrates the problem. To bridge the data gap between the initial design and final site delivery, we have to apply algorithmic constraint optimization. This means treating the factory not as isolated manual steps, but as a single mathematical equation. The Precast and Pre-Stress Concrete Slab Suite by Ferro-Fonds Digital acts as the unifying software ecosystem, engineered to resolve these exact pressure points. Transitioning to a predictive systems engineering approach allows a factory to model its entire capacity, ensuring production outcomes are deterministic rather than reactive. The first point of failure in a traditional factory is the design bottleneck. Estimators regularly spend days manually tracing walls on architectural PDFs and running manual calculations to determine structural loads. Ferro-Fonds addresses this at the front end with the Precast Layout and Support AI. Rather than relying on human tracing, the software uses AI-driven parsing to read structural DWG and PDF layouts, automatically identifying the load-bearing walls and required supports across the entire structure. It then analyzes the applied loads and span limitations to design the panels, confirming exact slab thicknesses and cross-referencing proprietary strand patterns. This entire output operates with mandatory human-in-the-loop verification before the data proceeds. Once the digital layout is verified, the challenge shifts to the physical floor. The constraints are unforgiving, managing multiple casting beds that are typically 100 meters long by 1.2 meters wide. The casting bed scheduler packs the total order book into this footprint. The nesting AI mathematically groups panels by thickness, pushing the casting area to its absolute physical limit. This generates a real-time wastage audit, allowing factory managers to continually tweak schedules and reduce raw material waste. Automating both the layout and nesting phases directly transforms a complex geometrical constraint problem into maximized raw material yield. Yet, even with mathematical precision, continuous casting inside a 100-meter bed inevitably produces offcuts, small splitter sections that are simply too short for the current order. The dynamic offcut inventory manager acts as a digital boneyard tracker, logging that isolated scrap into a database. This establishes circular manufacturing. When future projects need small infill strips, the application queries the boneyard first before suggesting a new cut. The data captured during this nesting phase feeds directly into the supply chain, governing the timing and scale of procurement cycles. This is handled by the Raw Material and Inventory Forecaster module. This chart visualizes the predictive intelligence extending from the order book. By utilizing time series forecasting, the software predicts exact requirements for cement, strands, and aggregates 7 to 30 days in advance. If a trend line crosses the safe stock threshold, the system automatically flags the upcoming shortage or potential overstock, completely preventing emergency procurement orders or sudden halts in production. Converting total wastage into monetizable inventory while predicting material needs with absolute certainty allows a mid-sized factory to heavily reduce its holding costs and optimize its operational cash flow. The final physical constraint occurs outside the factory walls, bridging the geographic gap to the construction site using heavy transport fleets. Transport logistics are bound by strict Department of Transportation weight maximums and the rigid physical dimensions of the flatbed itself. To navigate these boundaries, the software utilizes the Logistics and Stacking Optimizer. The intelligence here relies on reverse stacking logic. It calculates a loading sequence that guarantees the panels needed first by the site crane are positioned on the absolute top of the stack, while strictly adhering to the fleet's weight limits. Generating this exact loading schedule minimizes the total number of truck deliveries required and prevents the costly site delays that occur when a crane operator is forced to hunt for the right panel buried in a stack. The ecosystem also extends into niche, highly complex geometries. The pre-step staircase master automates the layout and SANS-compliant detailing for precast stairs, ensuring specialized assets don't interrupt standard production rates. Before any of this material moves, it must pass the final quality assurance gatekeeper, the Precast shop drawing auditor. This desktop application continuously cross-references individual drawing callouts against the master production schedule, catching minute errors in bar marks or slab dimensions before a single drop of concrete is poured. Once cleared, the system automatically generates a legal compliance certificate for every single panel, documenting the exact strand pattern, concrete mix, and curing date. Securing this level of compliance automatically strips hours of manual documentation from the workflow, severely restricts liability exposure for the manufacturer, and eliminates the industry's most expensive form of waste, factory reworks. The defining reality of heavy industry is that optimization cannot survive in isolation. If your nesting algorithm is perfectly efficient but remains completely disconnected from your raw material forecasting, the operational gains fail to scale. If a maximized casting schedule ignores the fleet's carrying capacity, you simply move the bottleneck from the factory floor out onto the highway. The power of the Pharaoh-Fons architecture lies in the master production schedule. It establishes a single, continuous digital thread that unifies architectural design, industrial production, site logistics, and legal compliance. It functions as the ultimate diagnostic and execution tool, empowering precast suppliers to cleanly bridge the gap between pristine architectural intent and raw physical reality. This moves the factory floor away from manual, reactive decision-making and toward a model of deterministic manufacturing. In the precast concrete industry, algorithmic constraint optimization provides the mechanism for extracting maximum capacity and